Okay, so this is the chapter on entropy. It's, the title of the chapter is called Spontaneity, Entropy, and Free Energy. We're going to learn new terms, new units, and I have a wonderful quote up here about the first and second law of thermodynamics. And the first law is you can't win, you can only break even. And the second law is you can't even break even. So this is kind of the overview of thermodynamics. Now when we do thermodynamics, we're actually combining chapter 6, chapter 12, and chapter 16. So we're going to be pulling some things back out of there. But when we talk about the first law of thermodynamics, that basically says that all of the energy in the entire universe is constant. It's not going away and it's not increasing. So the energy, and we're going to label that later on, we'll label that as universe. This is entropy symbol. So it's entropy of the universe, and that's the label that we're going to use. It's going to be a constant. Okay? Well, we use the whole idea of entropy and the first law of thermodynamics to try to keep records of what's going on.
So how do we find this constant?
How do you find this constant? This is not a constant. It's actually a change.
Of course it is.
It's delta E, or delta S, or delta H. It's delta. It's not a constant.
It's a constant. You just said it was a constant.
No, I said that the amount of energy in the universe is a constant. It's not a constant as in K, SP, K, C, or anything else like that.
A non-constant.
Mr. Leather, in the nuclear chapter, did we not determine that the energy in the universe is not constant?
No, no. What we learned is that the mass of something changes, but not the energy. The amount of energy in our universe is going to be a constant. It does not change. We're not increasing or creating more mass, and we're not destroying or getting rid of mass. So the amount of energy, the amount of mass, is all going to be the same in the entire universe. So we don't create energy or destroy energy. Energy is a constant, and the amount of energy in the universe is a constant. What we do is we change the energy from, potential energy to chemical energy to heat energy. We're going to change the form, but the total amount of energy in the universe is a constant. Bobby?
If the universe is forever expanding,
Drew. Do what?
Okay, if the universe is forever expanding and some of the energy is being distributed around there, can it expand so much to where it's spread out so much it's virtually nothing?
That sounds like a question for a theoretical physicist.
Let's go.
Teeth were slipping. So we're not going to address that in here.
Do you have dentures?
Okay?
He said my teeth are slipping. Actually,
Of course, there was the answer.
Okay?
There's the answer.
All right. So these are just a few formulas for review. This is all out of chapter 6, I think these are out of. So these are things that just keep in mind. You want to write them down to review them. They're generic formulas. Delta E, what does delta E stand for? What does E stand for?
Change of energy.
It's energy. It basically translates into heat. So we're looking at the heat in a system. The system is usually what we're focusing on. The system could be the equation, or if we go back to chapter 6, we had calorimeters, so the system is inside the calorimeter, and so we're looking at that system. And there are two ways that energy gets moved around. It gets moved around in the form of heat, which is Q, or the system does work. So work is a form of energy, and those two are going to give you the total internal energy for the system. So we also have a term W, which stands for work, and work is defined as the pressure, and this is internal pressure, it's not external pressure, times the change in the volume. And we also have enthalpy, H, and enthalpy is equal to the internal energy plus the value for work, so this basically has been substituted in here. And then you guys remember this from the virtual chemistry lab we did, where Q equals MC delta T. Q stands for heat, M is the mass, C is the, remember what C was?
Constant.
Specific capacity or heat capacity for that particular compound, whatever it is, and then the change in temperature. All right, so we're going to make an effort to understand what spontaneity is. I know you guys like to make jokes about spontaneity, but spontaneity or spontaneous is an actual concept that we have to understand entropy, understand Gibbs free energy, and all these other things. All reactions are not spontaneous. We're actually going to be calculating and finding out if it's spontaneous in direction as it's written, or spontaneous in a reverse direction, or if it's in equilibrium, it's not spontaneous. So we're going to do that. But spontaneous is a reaction that will occur without any outside force. And your book uses the example of iron and water and oxygen. You take a piece of iron, lay it out here outside right now, it's going to get wet, it's going to rust. It's going to happen. Okay? That means that reaction is spontaneous. And that particular reaction is spontaneous in that direction. It's not spontaneous in a reverse direction. Nobody yet has come up with a way of making rust turn back into iron and water and oxygen. It does not happen that way. Okay? It happens in that direction. So that would be spontaneous in that direction.
So,
Taryn? Okay.
If it doesn't go in the reverse direction, there's no equilibrium.
Well, what we're doing is we're looking at entropy. And entropy is an increasing order, a disorder in the universe. So when we talk about these things, yeah, you can't make it go in reverse, but there are equilibriums for some reactions. It depends on the reaction, depends on the stuff. Your book also mentions the idea of if you take a diamond and you put it down on the counter, it's a spontaneous reaction that diamond will turn to graphite. Okay? It doesn't mean fast, and it's not going to happen in our lifetime, but it is a spontaneous reaction. Okay? And I've already mentioned this. We're going to use some stuff from Chapter 6, which was thermal chemistry. We're going to use some stuff from Chapter 12. Chapter 12 was the one that everybody loved, all the rate laws and everything like that. We'll pull a few of those back in. And then Chapter 16 is all about entropy. Okay? Basically looking at this chapter, it's called thermodynamics. And what we're talking about here is the direction that the reaction is going to occur in. The Chapter 12 is going to be the speed. That's your kinetics. That's the rate, how fast it's happening. So when we talk about the direction, you aren't concerned with the pathway. The pathway is, okay, if I go from diamond to graphite, what happens in between? Thermodynamics does not worry about that. Thermodynamics only looks at where we start and where we end. And they use in the book, they do a good job of putting formulas in the book, but when they're talking about something, they're talking about entropy, they're going to take the final minus the initial to figure out, where the entropy is changing. A lot of times what they're going to do is rewrite this. They're going to take the entropy of the reactant and subtract the entropy of the products. So this would be the final, this would be the initial, because in a reaction that's what's going to happen. So when they're looking at entropy, they're talking about some of those values. Question over here?
Yes, if it's spontaneous one direction, does that mean it'll never be spontaneous in the other direction, or is that possible?
Probably. I was watching Rafi again last night, and I was reading through the book, and, you know, it just says it's not going to happen in reverse, I never say never. But, you know, the probability that it happens is so extremely large a number that it's just probably not going to happen. So yeah, so you can take that assumption, okay?
So is the only reaction that will have an equilibrium, are they like diamond and graphite, where graphite can turn into diamond and diamond can turn into graphite?
That's not going to be an equilibrium, because the graphite's never going to turn back into a diamond under standard conditions.
Okay.
So I guess I forgot to mention that, but you got to have those particular conditions in order for that to be spontaneous in one direction. Now, if you change the conditions, you put graphite under a great deal of pressure, then you can, you know, put it back into the diamond form.
But then it's not
But then it's not under the standard conditions. But
Then it's not spontaneous.
then it's not spontaneous.
Because it's because that's outside interventions.
Right. So, a process that's spontaneous in one direction will not be spontaneous in another. This is out of your book. Again, I don't like to use the word never happens, because there's always that one chance in a billion that it will happen. You know, and they use the example in the book, like, if we can take wood and burn it into carbon dioxide and water, why can't we take carbon dioxide and water and put it back into wood? Well, we do, but it's under different conditions. And that's when a plant takes the carbon dioxide and the water in and makes new wood. But it's not the original wood, it's a different wood. So they do happen in the reverse direction. But for this chapter, for thermodynamics, if it's spontaneous in one direction, it will not be spontaneous in the other direction. Because we're actually going to calculate, and we're going to look at the sign of the delta S, and the delta S for the universe is going to tell us, is it spontaneous in a forward direction, is it spontaneous in a reverse direction, or is it at equilibrium? Okay? Processes are going to occur without outside assistance. That's where we take a piece of steel, put it out there in the rain right now, and come back tomorrow, and it'll probably be rusted. Independent of time. So time is not a factor. And you get the idea of time not being a factor if you just put that diamond on the table. It's going to turn. Common characteristics for this is the spontaneity. We measure it. It's called entropy.
Bless you.
And I have, coming up on the next slide, I've got about 6 different definitions for entropy. We can define it lots of different ways. The symbol is S. And if the change in entropy for the universe is always increasing, why is it always increasing? Well, we can take the whole idea of the Big Bang. Okay? Our universe started from a small condensed mass. Listen to the theme song on Big Bang Theory.
The whole universe.
Yeah. So it's expanding, which means it's going outward, which means it's going to greater disorder. And so that number that's calculated for the universe is always going to be a positive number. That's for the universe. So if we're going to get to this formula in a little bit, delta S for the universe is equal to delta S for the system. That's going to be the reaction we're looking at, plus delta S for the surroundings. Okay? This is always going to be a positive number. Now, we could have, well, it could be a negative number, but that's going to be for the reaction. But for the universe, we're always going to have an increase in entropy.
I'm confused.
Okay, out of confusion and chaos comes understanding and enlightenment, and it's one of my favorite quotes that I made up years ago.
If the energy of the universe is constant, how can it change?
Energy doesn't go away, and we can't make new energy. So the energy in the universe is constant. In other words, all the energy that we'll ever have is there right now. The problem is it's in a form that we can't use. So if we're talking about this thing has potential energy at this point in time. Now I release it, that potential energy is gone someplace. Well, what happens is it's gone, it's lost a little bit of friction to the environment, the molecules, the atoms that it passes by. Some of it is going to be created into a different form of energy in the table. It still has a little bit of potential energy because it's on the table and not on the floor, but it's lost some of its potential energy. But that potential energy gets converted to some other type of energy. So we're not creating energy or losing energy, it's changed to something that we can't use anymore.
I get that, I don't know what my question is.
Okay.
I understand what you just said, so we can,
Okay.
I'll try
So-
to think of it.
Would the center of the Earth not have any potential energy, like the exact center?
It wouldn't have any potential energy of position, but it's going to have a potential energy for the chemical construction. You've got a tremendous amount of pressure, you've got all kinds of chemicals being created and breaking apart there, so it's got a lot of chemical
So
energy.
you always have.
But see, it still has the energy, and the energy is just in a form that may or may not be usable. That's the key that we're all looking
So
for.
you always have potential energy. You can't ever get rid of that.
But it
Okay.
would just have
Well,
no
I mean,
gravitation.
No,
change the
it's
form.
at
Right.
the center of the earth.
You would have the potential energy to.
I mean, if you
be
cause
laser
something
burst
to
or
react, then it loses that.
But it says high
Everything
state
gets-
kinetic energy, it has no potential energy.
Right.
It has
So it
to-
has to have maximum.
Has chemical energy.
If it's,
But at that
Okay.
position, it would have
So
no.
here's some definitions. There's several different definitions here for entropy. Okay? A measure of molecular randomness or disorder. I mean, you get that from the Big Bang. The Big Bang is that all the molecules in the entire universe were at one time compact. They were very, very ordered. And as the explosion occurred, they become disordered, more random, spreading out, going away from each other. So if you look at all the molecules, atoms, and everything else that make up our entire universe, there's a huge amount of disorder out there. And high disorder gives you high entropy. So the more disorder you have, the bigger your delta S is going to be. In thermodynamics, we're going to use this concept to describe what are the possible places that these atoms could be. We're going to look at a little probability here in just a few minutes to kind of get an idea on that. And it is probability, it's mathematical. If I have a solid, such as a marker here, it's pretty well ordered. But if I change the marker to a liquid or to a gas, the disorder is going to increase, especially when I get to the gas, it's going to increase exponentially. I always kind of like to favor this one here, a measure of chaos in a system. You know, and to me, a lot of times, the class seems like it's chaos. You're very, very quiet and well behaved today. I don't know why, but that's okay. Probably because it's being videotaped. Justin?
So,
So we'll have proof that you are in chaos when you're in class if I have a video on.
so, like, a more complex atom would have less entropy?
Yeah.
So,
But-
like, glucose would have less entropy than.
You also have the whole concept, if you take that combustion reaction, where we're going to take some hydrocarbon, we're going to take glucose in this case because it's an easy one to write, and we're going to combine that with oxygen, and then that reaction is not going to be in equilibrium, I'm used to writing that, is going to end up with CO2 plus H2O. Well, if you were to measure the energy for those compounds, the energy that's here and here is going to be up here at some point. After the reaction occurs, the new compounds, their energy on the energy scale is down here. So these have a whole lot more energy than these. So we're changing the energy here, and that energy, as you well know, makes you nice and warm. It produces heat. So one of the products for this reaction is going to be heat. So, driving force for all this stuff is spontaneous processes. Yeah.
What does entropy tell us? Like, what's the point?
anything else in the system?
Well, we can use the concept of entropy to actually figure out if a reaction is going to be spontaneous or not.
I feel
And
the necessity of that.
as far as you and your everyday life, I don't really know. It's an area where like physicists like to play around.
This is your fault.
Too bad Chris is in
It's all
here.
your fault. Okay. All right.
You can borrow the shirt at any point in time.
Yeah. So, entropy ain't what it used to be. And that's part of the second law. So the amount of entropy out there is always increasing. The universe is going to a greater state of disorder. Or as this one over here says, you can't even break even. So in the first law of thermodynamics, we're talking about the amount of energy in the system. You can't win. The energy, you cannot create more energy. You can't lose energy, you can't create more energy. So all you can do is basically break even. The energy there is going to be there. It's going to be in different forms. Well, when you get to the second law of thermodynamics, basically what they're saying is the amount of entropy is going to be increasing. Well, that means you can't even break even. Think about the energy in a gallon of gasoline. It's got so much energy in there. Okay? First law says that is going to produce X amount of energy. We can figure that out. The problem is that when we convert it, it goes from a chemical energy to a heat energy, and when you put it in your car and you burn it, you're losing heat energy. That's just a different form of the energy that's in the gasoline. We're not getting all the energy in the gasoline into driving the car. Some of that energy goes into heating the engine up, and we're losing that energy. So you can't even break even. You can't take a gallon of gas and get every single bit of the energy in that gas directly transferred into a car engine, because we're going to lose it as heat. So that's where we can't even break even, because now, no matter what energy we start with, we're going to be losing some of that energy to a form that's not usable.
What if, like, I know this isn't possible, but a system with no friction? If it was possible,
Let's see, it's not possible. So we can't even entertain that question.
we entertain things that aren't possible with ideal gases.
That's theoretical, but it's not a practical system. Okay? Ideal gases don't exist. But we can entertain those ideas in a theoretical mode, but if you're trying to find a way to compensate, you know, we're getting better at it. We're getting a whole lot better. An electric motor has a very, very good efficiency system. So whatever energy we put into the electric motor, we're going to get about 90-some% of it back out. So it's much, much more efficient to drive our cars with electric motors than it is with gasoline combustion engines. With gasoline combustion, we lose energy. Electric cars, we get a lot of this stuff direct transfer. Batteries are going to give us direct transfer. All right. So, second law of thermodynamics, the entropy of the universe is always increasing. Total entropy must increase for any spontaneous process. So we're talking about measuring this entropy. You can define entropy in terms of probability. And this is basically what Las Vegas is built on, probability. Probability is always going to be for the house. You go to Las Vegas, you think you're going to make $1 million gambling, it's not going to happen because the probabilities are against you. Yeah,
It might
it's like
happen.
going out and buying a lottery ticket. Probabilities are against you winning. I don't know if you've ever looked at any of those things. But probability is a way of talking about the randomness of the particles and where that randomness shows up. So, are we done with this down here?
Yes.
All right. So, how many minutes are we looking at so far?
Almost at 25.
25? All right. I'm going to finish up with probability here in a minute, so, we ready? Yeah?
Yes.
All right. So, this is a little exercise in just looking at probability, because when we talk about entropy, excuse me, I'll get it out there. When we talk about entropy, we're talking about probability. So here's an example. If we take two containers connected by some little valve in here, and we put a single molecule in those total two containers, the probability of that molecule being over here and being over here, there's two different ways that it could happen. Okay? So there's process of finding where that gas molecule would be, or trying to predict where it would be. It's really a 50-50 chance. It's kind of like flipping a coin. If you take a penny and you flip the coin, how many times will you end up with heads and how many times will you end up with tails? Probability says that if you do it enough times, you'll get a 50-50 split. If you do it once or twice, you may get two heads in a row. But over a long period of time, probability says that it's going to end up with a 50-50 arrangement. So every single one of these configurations, this is referred to as a microstate for that molecule in those containers. So we've got two microstates here, two possible places for that molecule of gas. Now, we increase that by putting two gas molecules in there. What we end up with is 4 different microstates. So the top one there, the blue and the red are on the right. The next one, red is on the left, blue is on the right. The next one, those two are reversed. And the last one, the blue and the red are both on the left. So those are 4 different microstates. The more molecules you add into the system, the greater number of microstates you're going to end up with. Think about how many different possible combinations there would be if I put 100 molecules in here.
A lot.
You'd have a lot more than just 4 microstates. Okay? And that kind of gives you an idea of the probability. So in the universe, we have 6.02 times 10 to the 23rd whatevers. How many different possible places could they be? You will never ever end up with a situation where all the gas is on one side if you got a mole of gas. If you got 6.02 times 10 to the 23rd gas molecules and you put it into this microstates, you're never ever going to find it, all of them over here. And again, I don't like to say never. But the probability is really, really high that you will never, ever find them in one place. In your textbook on page 753, there's a table where they actually use 4 molecules. And then toward the bottom down there, there is an example of the two states of 4 molecules. But at the very bottom, it's going to show you where the probability of having lots of them in one side is just not going to happen. Now, as we look at these probabilities, we can apply that to other things. When they talk about a probability, they're talking about a positional entropy. Positional entropy, if we go back, this would be a positional entropy. This would be one possible microstate. So positional entropy is looking at those numbers, and it's going to depend upon how many different microstates you're going to have. So if you got 6.02 times 10 to the 23rd atoms, then I can't even comprehend what that number of microstates would be. However, you can relate this, I think, very well to the 3 different phases of the standard phases for different types of compounds. When you're looking at a solid, that solid has only one microstate. Solid. It's not like the atoms are moving all over the place. They're in one place and they're solid. If you go to a liquid, the liquid is defined by the container, but that individual molecule or individual atom in a liquid has many more places it can move. Solid doesn't. They're just rigid. They're held there with the electron, the flow of electrons around the metal of the solid. So We're gonna have more possible places for it if it's a liquid. If we get to a gas, the number of positions is just astronomical. The number of places that individual molecules. So in order of increasing S, we got a very, very small entropy here with a solid. We've got more entropy in a liquid than we do in a solid. When we get to a gas, it's almost exponentially larger for the entropy there. Okay. All right, let me go just one more slide because I want to talk a little bit about positional entropy. Substances with higher positional entropy. So if you look at this, carbon dioxide solid, carbon dioxide gas. What's that process called?
Sublimation.
Sublimation. So the process is sublimation. Which one has a greater entropy? The gas. Which one of these has a greater entropy? Nitrogen at 1 atmosphere versus nitrogen gas at 1.0 times 10 to the negative 2.
1 times 10 to the negative second.
Why?
Because it has less pressure, therefore it'll be more spread
More
out.
places to go.
Yep.
Less pressure, more places to go. And I think that's where I want to stop. So